Hello student, welcome to all of you in the next physics lecture. Myself Rajesh Lagat, physics teacher. Now in this gravitation chapter, the next point is very important. That is the statement for the Kepler's laws of motion. If you have to ask this, state the Kepler's laws in motion, then you can write the three laws of Kepler's laws in motion. The first statement of the Kepler's law is that every planet, we have to write here, every planet revolves in an elliptical orbit around the sun. Every planet revolves in an elliptical orbit around the sun, and with the sun is situated at the one of the focus of an ellipse. At that time, the sun is nothing but what? Focus of an ellipse, or the foci of an ellipse. At that time, this every planet revolves in an elliptical orbit around the sun. Okay, this is the first statement of the Kepler's law. Again, you have to repeat this statement. Every planet revolves in an elliptical orbit around the sun, with the sun is situated at the one of the focus of an ellipse. Okay. Second law is that the radius vector, you know that this radius vector, that is a line drawn from the center of the sun to the planet, and which describe equal areas in equal time, and which is also, in other words, we have to see here the aerial velocity. This is nothing but what? The aerial velocity, and which should be remains constant. In short, this second law of this Kepler's second law, we have to state here only the aerial velocity is remains constant. Again, then what is mean by this aerial velocity? That is the radius vector, that means the line drawn from the center of the sun to the planet, which describes in equal areas in equal times. That is, the aerial velocity should remains constant. This is the second law. Now third one is that the square of period of revolution of the planet, square of, that means t square. In short, we have to remember here the t square. Square of period of revolution of the planet around the sun is directly proportional to cube of semi-major axis of the elliptical orbit. Semi-major axis of the elliptical orbit. In short, we have to remember this third law of Kepler's third law. T square is directly proportional to r cube. What is this t square? The square of period of revolution of the planet around the sun. Square of period of revolution of planet around the sun, which is directly proportional to cube of, r means what? This is the radius of the semi-major axis. That is the cube of the radius, that is the semi-major axis of an elliptical orbit. That is the t square is directly proportional to r cube. This is nothing but the third Kepler's laws of motion. These are the three laws of Kepler's laws of motion. Okay. In your exam or general knowledge, you have to remember these three laws, Kepler's laws of motion. Again, we have to repeat these three laws. First law is that every planet revolves in an elliptical orbit around the sun, with the sun is situated at the one of the focus of an ellipse. Second one is that the radius vector, that means the line drawn from the center of the sun to the planet, which describe the equal areas in equal times. In other words, we have to also state this, the aerial velocity, which should be remains constant. Okay. And third Kepler's law is that the square of period of revolution of the planet around the sun is directly proportional to cube of semi-major axis of an elliptical orbit. In short, we can directly write t square is directly proportional to r cube. Okay, these are the Kepler's laws. Now we have to see here the projection of satellite. Okay, how the satellite can be projected. In this projection of satellite, we define the definition of an satellite. An object which can be revolves in an orbit around the planet is called as the satellite. And Moon is the natural satellite. Okay, you know that Moon is the natural satellite. Then what is meant by the artificial satellite, which can be the made by the man? This is nothing but the artificial satellite. And you also know that the first artificial satellite made by the man have been launched on the 4th October 1957 by the USSR, Union Soviet Sangh, Russia. And our nation, India, was launched the first satellite. Name of that satellite is Aryabhat, and date launching on the 9th April 1975. And this artificial satellite, which can be the used for the various purposes, these are the very important, such as telecommunication, television and broadcasting, then meteorology, and the weather forecasting. All these purposes, this artificial satellite can be the uses. Now, how this satellite can be the launch? Should be the two stages for launching of the satellite: single stage rocket system and the multi-stage rocket system. But initially, we can use the this single stage rocket system. Then there should be the uh, rare case. There should be the this satellite can be the fall on the Earth surface. Sometime it's happened if the velocity attained by the satellite, which is the less than escape velocity, then and then this satellite should be fall on the Earth surface. It should be very dangerous. So that the we can our safely the this rocket can be the launch by using the multi-stage rocket system. In order to launch this satellite in orbit around the Earth, the multi-stage rocket system is used, and the satellite can be the place at the tip portion of the rocket. Initially, the fuel in the this rocket in the first stage it should be ignited, and so that the rocket rises to the desired height, and with the help of the remote control, the first stage of the rocket it should be the detach, when the fuel in the first stage should be the completely burned. Then automatically the second stage of the this rocket should be the started ignited, and so that the rocket should be the push in a horizontal direction, and again the fuel in the second stage is completely burned. Then this empty stage also detach from the satellite, and this resulting motion of the satellite depends upon the horizontal velocity, and which is completely along with these four cases. These four cases are given below. If the horizontal velocity, these four cases are here, and first case is if the horizontal velocity attained by this satellite, which is less than the critical velocity. We have to separately see this point, critical velocity, but you have to remember here only the horizontal velocity attained by the satellite, which is less than the critical velocity, then this satellite moves in a parabolic path. Then this satellite, which can be the revolves in a parabolic path. This is the parabolic path as shown in figure. Okay, this is the parabolic path. We have to say here the number 1. If the velocity attained by the satellite, which is the less than the critical velocity, then and then this satellite can be the revolves in a what? Parabolic path. Okay, underline this parabolic path. Second one is that if the velocity attained by, that is the horizontal velocity attained by this satellite, which is the exactly equal to the critical velocity, which is the exactly equal to the critical velocity, then this satellite can be the moves along the a circular orbit as shown in figure. This is the number 2, case number 2, and this satellite can be the revolves in a circular orbit. Okay, when second condition is that what? If the horizontal velocity attained by the satellite, which is the exactly equal to the critical velocity, exactly equal to the critical velocity, then this satellite can be the moves in a circular orbit. Okay, along the circular path. This is as shown in figure. This is the second. This is arrow. This case second. Okay. Third case is that if the horizontal velocity attained by the satellite, which is the greater than the critical velocity but less than the escape velocity. Condition is that horizontal velocity is greater than critical velocity but less than escape velocity, then and then this satellite, which can be the moves in an elliptical orbit. This satellite can be the moves in an elliptical orbit, which is also as shown in figure. This is the case number 3 arrow. This is the third number, case 3. If the velocity attained by the satellite, which is the greater than critical velocity but less than escape velocity, critical greater than critical but less than escape, then the satellite is moves in an elliptical orbit like this. This is an elliptical orbit. Okay, and last one is that if the horizontal velocity attained by the satellite, which is the greater than critical escape velocity, horizontal velocity attained by the satellite, which is the greater than escape velocity, then and then this satellite leaves the earth gravitational field. That satellite which can either escape from the earth gravitational field and escape into the space. And this is nothing but the fourth case. That is, if the horizontal velocity is greater than escape velocity, then and then this satellite, which can be the escape from the earth gravitational field, influence of the earth gravitational field, and escape into the space or projected into the space. And this is the fourth one case, which is as shown in figure. Okay, so these are the four cases how the satellite can be projected into the space. Okay, you have to understand. We can stop here.